Welcome to this presentation on Period 3 of the periodic table. Today we will look at the properties of Period 3 elements and their oxides. We will explore how their physical properties, bonding, and reactions change across the period. A-level specification focus and learning objectives, the Period 3 elements and electron configuration, general patterns, and predictive power of periodic trends. Period 3 elements are sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, and argon. They show a gradual change from metals to non-metals across the period. Period 3 consists of 8 elements: sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, and argon. Across the period, the proton number increases by 1 each time, while electrons are added to the same principal energy level. This means that shielding from inner electron shells remains relatively constant, which is a crucial idea when explaining trends. Sodium begins the period with a single electron in the 3s subshell, making it highly reactive and metallic. Magnesium and aluminium also have electrons in the 3s subshell, but increasing nuclear charge leads to stronger attraction between the nucleus and delocalized electrons. Silicon marks a major change, as it forms a giant covalent structure rather than metallic bonding. Beyond silicon, the elements phosphorus, sulfur, and chlorine exist as simple molecular substances, with covalent bonds within molecules and weak intermolecular forces between them. Argon, as a noble gas, is monatomic and chemically inert due to its complete outer shell. As nuclear charge increases across the period, there are clear and systematic changes in physical and chemical properties. Atomic radius decreases, ionization energy generally increases, metallic character decreases, and oxides change from basic to acidic. For instance, while ionization energy increases overall, there are notable dips at aluminium and sulfur that must be explained using subshell energy levels and electron pairing. Atomic radius across period 3, first ionization energy and its anomalies, melting points, and underlying structure. Atomic radius decreases across period 3 from sodium to chlorine, and this trend is a classic example of how nuclear charge influences atomic size. As each successive element has one more proton in the nucleus, the positive charge increases. At the same time, added electrons enter the same principal energy level, so there is no significant increase in shielding. This means the outer electrons are pulled closer to the nucleus, resulting in a smaller atomic radius. For example, sodium has a relatively large atomic radius due to its lower nuclear charge and weaker attraction for its outer electron, whereas chlorine has a much smaller radius because of its much stronger nuclear attraction. Argon's atomic radius is often less clearly defined because it does not form covalent bonds, but the overall trend remains decreasing. The first ionization energy generally increases across period 3 because of increasing nuclear charge and decreasing atomic radius. As the nucleus becomes more positively charged, it attracts the outer electron more strongly, making it harder to remove. The drops from magnesium to aluminium and from phosphorus to sulfur. The drop from magnesium to aluminium occurs because aluminium's outer electron is in a 3p subshell, which is higher in energy than the 3s subshell in magnesium. This electron is therefore easier to remove despite the increased nuclear charge. The drop from phosphorus to sulfur is due to electron pairing. Phosphorus has 3 unpaired electrons in its 3p orbitals, whereas sulfur has 1 paired set, leading to increased electron-electron repulsion. This repulsion makes it easier to remove 1 electron from sulfur. The melting point trend across period 3 is complex because it depends heavily on the type of structure and bonding present. From sodium to aluminium, melting points increase because of stronger metallic bonding. As the charge on the metal ions increases and the number of delocalized electrons rises, the electrostatic attraction between ions and electrons becomes stronger, requiring more energy to break. Silicon has a very high melting point because it forms a giant covalent structure, in which many strong covalent bonds must be broken to melt the substance. After silicon, melting points drop sharply because phosphorus, sulfur, and chlorine are simple molecular substances. In these elements, melting involves overcoming weak intermolecular forces rather than strong covalent bonds. Sulfur has a higher melting point than phosphorus and chlorine because it exists as larger S molecules, which have stronger London dispersion forces. Argon has the lowest melting point because it is monatomic and only experiences very weak dispersion forces. Metallic conductivity in sodium, magnesium, and aluminium, semiconducting behavior of silicon, non-conductivity of molecular and noble gas elements. Sodium, magnesium, and aluminium are all metals and conduct electricity in both solid and molten states due to the presence of delocalized electrons. In metallic bonding, Positive metal ions are arranged in a lattice surrounded by a sea of delocalized electrons that are free to move throughout the structure. When a potential difference is applied, these electrons can flow and carry charge. Conductivity increases from sodium to aluminium because the number of delocalized electrons increases and the ions have a higher charge, leading to stronger attraction and a more robust metallic structure. Silicon has unique electrical properties because it is a semiconductor rather than a good conductor or an insulator. It forms a giant covalent structure in which each silicon atom is covalently bonded to 4 others. At low temperatures, there are no free charge carriers, so silicon does not conduct electricity well. However, as temperature increases, some electrons gain enough energy to move into conduction bands, allowing limited conductivity. Phosphorus, sulfur, chlorine, and argon do not conduct electricity under normal conditions because they lack mobile charged particles. These elements exist as simple molecules or, in the case of argon, as monatomic atoms. Although there are covalent bonds within the molecules of P, S, and Cl, electrons are localized in these bonds and are not free to move through the substance. Argon atoms are held together only by weak London dispersion forces and also lack any delocalized or mobile electrons. Basic oxides, sodium oxide and magnesium oxide, amphoteric behavior of aluminium oxide, acidic oxides of silicon, phosphorus, sulfur, and chlorine. Sodium oxide and magnesium oxide are examples of basic oxides found on the left-hand side of period 3. Both are ionic compounds containing oxide ions, O², which readily react with acids. Sodium oxide reacts vigorously with water to form sodium hydroxide, producing a strongly alkaline solution. Magnesium oxide is also basic but is less soluble in water, so it forms a weakly alkaline solution. The difference in solubility can be explained by the higher charge density of milligram-squared ions, which leads to stronger ionic bonding and a higher lattice enthalpy. Aluminium oxide is amphoteric, meaning it can react with both acids and alkalis. This behavior reflects aluminium's intermediate position in period 3, where metallic character is decreasing and covalent character is increasing. Aluminium oxide reacts with acids to form aluminium salts and water, and it also reacts with strong bases such as sodium hydroxide to form aluminate ions. On the right-hand side of period 3, oxides are acidic and predominantly covalent. Silicon dioxide is a giant covalent structure and does not react with water, but it does react with hot concentrated alkalis. Phosphorus V oxide reacts vigorously with water to form phosphoric acid. Sulfur dioxide and sulfur trioxide dissolve in water to form acidic solutions, contributing to acid rain. Overall trends in oxide-acid base character, using graphs, data, and comparisons in exam questions, key takeaways, and final exam tips. A central theme of the period 3 topic is the clear trend in oxide behavior, moving from basic through amphoteric to acidic as you go across the period. This trend reflects decreasing metallic character and increasing electronegativity. On the left, ionic oxides contain oxide ions that readily accept protons, making them basic. In the middle, aluminium oxide shows mixed behavior due to its partial covalent character. On the right, covalent oxides react by forming acids in water or by acting as proton donors. Graphs and data tables are included related to period 3 properties, such as ionization energy or melting point. Students must be able to describe trends accurately and then explain them using chemical principles. This involves identifying overall patterns, recognizing anomalies, and providing detailed explanations using appropriate terminology. For example, when presented with an ionization energy graph, students should mention nuclear charge, atomic radius, subshells, and electron pairing where relevant. To summarize, across period 3 elements change from metals to nonmetals. Bonding changes from metallic to giant covalent and simple molecular structures. Their oxides change from basic to acidic. Thank you for watching.